Entonces, quizá les recuerdo también que los mensajes también quedan grabados, ¿ya? Quizá ustedes ya saben, pero en el fondo el ejercicio de desarrollo eran dos ejercicios, pero que en verdad eran iguales, ¿ya? Quizá podríamos haberle dedicado un poco más de tiempo y haber hecho dos ejercicios distintos, pero la idea era que fuera también justa la evaluación, en el fondo, que no hubiera un ejercicio que fuera más difícil que el otro. Pero ambos ejercicios eran una estructura semicircular que estaba apoyada en dos puntos fijos, ¿ya? Eh, Quizá debería haber usado otro color. Ya, y esta estructura era una sección de círculo de ángulo teta. Y en estos puntos fijos, normal a la estructura, tenía dos reacciones. Las reacciones tenían que ser normales porque esto estaba curvado. Entonces, esto podría haber sido o Hoover Dam. Perdón. Eh, Voy a pasar a inglés ahora. So, this structure could have been Hoover Dam or the
Solo
Storm
una
Gate.
cosita antes, que
Sí,
creo que
dígame.
está haciendo desarrollo, pero no está compartiendo como su iPad.
Gracias, gracias. Sí, 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 sí. Tengo que cambiar la cámara. Gracias. Sí, ¿se ve ahí?
Ahí sí, profe.
Ya, perfecto. Gracias. Okay, so there was this structure which was curved, like a section of a circle, and this section had an angle theta. And if you had a look at this symmetry plane, it would look something like that. So you had the structure here. We said that the bottom was flat, and we said that on one side of the structure you had certain water big H, and at the other you had little h. And this was common for both structure, the gate and the dam, right? So that was it, and you were asked to compute three things: the total, the resultant force of the hydrostatic pressures, the point of application of this force, and the reaction forces on these hinges, or I don't know, on the extreme points of the structure. So what was new here? It wasn't a trick though, but probably this was a bit new, but many of you got it right, is that you had a pressure distribution at both sides, right? So you could compute like a resultant or a net pressure distribution would look something like that. It would be linear up until this point and then uniform, because you had at both points, at both sides, increasing pressure on linearly increasing pressure. So you could see it like this, or you could say, okay, this water body creates a certain force, and I'm going to call this F1, and this other creates a certain force, F2. So the resultant force is nothing more than F1 minus F2. Here you have to be consistent. If F is pointing in this direction, then this is the rest, right? If it's pointing in the other direction, then it's the other way around. You might already know that F1 is larger than F2. So, just to keep everything positive, this was the way to compute F. You could know this without even computing F, right? And also, as someone said during the test, well, there is a geometric thing here. There's two things that you should have seen. You should have seen, let's say, the distance, the horizontal distance between these 2 points. Let me call this, and we said this was L, right? The diameter of this sphere or circular arc was L. So this distance, let me call this W. You can call it, or maybe B, because W could be weight. Okay, this distance B B is 2 times sine of theta half, right? Because this angle is theta half, so uh this is right. Yeah. So this is sine L uh L sine theta half, and this is 2 times that. So this is the distance between those two. And the other thing you could have seen directly is that you could project these resultant forces R into this horizontal plane. This is a symmetric uh, problem. So on the plane, you would you didn't have to argue actually that F was going to act into this the symmetry plane. So if you decompose R here, you're going to have directly that F has to be equal to 2 times R cosine of theta half, right? And therefore, R is F divided by 2 cosine theta half. Okay, so you could do this without knowing anything about fluid statics or fluid dynamics, right? This is
Profe,
just yes.
su pantalla se ve al revés.
Oh, let me now.
Sí, sí.
Okay, thank you. Okay, so like I said, you could have written this and this like right from the start without even knowing one thing about pressures or anything like that. Uh, and that would have given you some points. Of course, the larger part of the question is determining F. You see, if you determine F, then you can determine R, and a whole new thing is where is F acting. Okay, so what is F? We said it's F1 minus F2, but what is F1? Well, F1. If you look at this, maybe I'm gonna draw it again just to make it clearer. If you have a certain water depth at H, then uh, F1 is nothing more than gamma H half, because that's the point, the center of pressures, right? Which is midpoint between the top and the bottom, times the area, and the area is H times B. Why B and not this area? Well, because it only matters the projected area. So at if you look at this gate from this point, you don't see all this area. You only see the projected one, which is this, right? The projected distance. So B times H is the projected area. Okay, you could have compute, let's say, the pressure in a infinitesimal uh, a very small section of the gate, and then integrate all these very small forces. And that would be right, but you would need to realize that this force acts normal to the gate. So you need to decompose it on the vertical and on and horizontal and vertical components. And when you do that, you end up really computing the forces along this straight line. So that was uh, into this curved surfaces section. So you should have known this. And again, B is just geometry. So F1 is nothing more than uh, gamma H B2. half, right? And you can see if f2 is just the same thing, right? But with h small. So big F is just the rest of these two. So it's gamma b half h square minus uh, h small square. And this was the total force. Okay. This part is clear. I have no problem explaining it again.
I have a question
Yes.
about the big F sorry, the big B.
Yeah.
Where it does come from?
This one. This is
Yeah,
the,
yeah.
let's say, look, let's say you have, let's forget about this for a moment. Let's say you have water here and you have ball floating. Let's say there was a, there was an, it has a, let's say a string, so it's tied to the bottom. You have to realize that the lateral force is nothing more than the projected area. So along this area, there is a force acting that way. And of course, this is the same on that direction. So the net lateral force is zero on a submerged body. Uh, but the lateral force only depends on the projected area. You could compute the force on each individual point into the sphere. But when you do that, and this was also the trick in the homework, let's say, once you compute the force into a small infinitesimal area, you have to decompose that force into its three components. So you're going to have one component in, two components on the horizontal and one on the vertical. So this B comes from, if you look from, in this case, from the reservoir or from the storm side of the gate, uh, the total width of the gate is not really the width along the gate, but just the projected width. Okay. Now that doesn't mean that there is no force, but you need to realize that some of the forces acting on the actual gate are nullified. So let me exaggerate the shape. If you do this, you're gonna have forces acting normal to the gate at every point. So you see, this force is going to cancel this other, but only the vertical component, and they're both going to add a little bit to the lateral component. Of course, this add totally, but the vertical component of this piece cancels out with this one, and you only end up adding this one. And if you do the integration, I mean, you can do this. If you go and actually integrate the delta force acting on this, on each of these things, but force as a vector, you're gonna end up with this very same equation. So the only important area is gonna be the projected area. Okay. So so that was the first question, and the other question was, where is this thing being applied? And here again, some of you might have been tempted, or might have wanted to use this equation, right? I don't recall. I think C. No, this is just G times the moment of inertia divided by the area, something like that. I'm not even sure. I think it's this one. But you need to realize, and I told you this in the last class, here y is measured from the free surface. So when you had when you have this, you could have computed this one for 1 and 2, but both would have been drawn from different points on the vertical. So this yc would have been this distance, and this distance from the free surface, which is different on each side. Of course, you could have said, well, this is just this difference, h minus h.
Profe, una
Yeah,
cosita.
yeah.
¿Cuánto valía la fuerza resultante total?
I just deleted, but
Me parece que escribió gamma seno teta medio L H menos H, ¿no? Algo así.
give me a second. The total force is gamma b half h square minus h square. Yeah,
¿Y eso en qué
and
dirección va?
this direction.
Ah, en esa dirección.
So
Entonces,
it's coming in into the center of the how do you say the center of this radius,
ya, perfecto.
right? So that was on x, if you want, or on the horizontal. So actually the question was on the vertical, where is the point of application? Because you could have argued this position just by symmetry. You could have also integrated yourself. I mean, you could have done that, but it's pretty clear, and I told you during the test that it was pretty clear that this was symmetrical. Okay, so you could have used this equation, but you had to keep in mind that both yc1 and yc2 were referring to different vertical datums or vertical reference. So you needed to keep that in mind. Many of you, though, realize that uh, the center, the point of application is just h third at each side, which I also told you during class, right? And if you knew that, I mean, you could have computed this and then subtract the total water depth, and then you're referring everything to the lower to the bottom. Uh, but if you can also just put h third because that's the center of mass of a triangle. I mean, you could use that as a given. So if you use that, then the total application measured from the bottom, I'm going to call this y, but from the bottom. So the total point of application times f has to be equal to f1 times I1 minus f2 times I2. This is just a torque summation. So this is a positive torque. This is a negative one, and we are assuming already that f. I mean, we know f is f1 minus f2, so it's going to be positive 2. It's going to be in that direction, right? And from here, just y is just f1 h third minus f2 h small h third divided by total f. And then you could have just replaced the values, and you end up. Let me just filling. Okay, you end up, if do the algebra, you end up with 1/3 h to the cube minus h small to the cube, then h squared minus h squared. And that was it. So it wasn't an impossible exercise. It wasn't that different from what you have seen on the book or on the recitations, but you needed to be aware of several key concepts that I can give you. It wasn't a one thing. But then again, I think it wasn't either rocket science. I mean, many of you, at least some 4 or 5 people, got it fully right, and many of you got it mostly right. Uh, but I don't know if so. That was what you needed to respond. But if you have comments about this is a good time.
B es solamente la mitad de ese largo, ¿no?
No, it's the full length. This is B. And B, I think I put it somewhere. Let me
Es que
just-
como analizamos teta medios, por eso tenía la duda de
You could have done, yeah.
¿por qué no era dos
No, no,
veces?
no. B is the full length. So B is here it is. B is 2 times sine to the half, right? So B, maybe I'm this is a bit messy, but this side is just L sine to the half, and this other side is the same. So B is 2 times this. So
Ah, ya,
B
sí, esa era la duda. Es que pensé que
yes.
al otro lado pensé que era una L solamente y no era dos veces. Ahí sí.
No, no, no. It's 2 times. Oh, yeah. It's 2 times L. Yeah. So B is the full distance between these two. So it doesn't matter the shape of the gate. Could have been, could have been like that. It doesn't matter. It only matters the full projected distance. This is only relevant for the internal forces of the structure, which we're not going to get into here in this course. But if you are civil engineers or structural engineers, then it is important, and it's one of the reasons why these structures are curved. So the normal you only have compression forces, and all the reaction force uh, passes through this point. By the way, I forgot to look at it, but yesterday they closed this gate in the Rotterdam port. They do it every year. It's a big event, and people can go and take pictures. This year, of course, it wasn't public, but you can watch it on streaming. I mean, it already happened, but I'm assuming it is recorded. I forgot to look it before the class, but I'm gonna look for it later, and I'm gonna post you a link if you are interested in watching this huge thing closing. Uh, so basically, they close it and they wait for the tide to rise, and just checking that the thing works properly. And then when the tide goes down and the water level at both sides are the same, they open it. So you don't create a small tsunami. Okay, any questions about this question or about the test? Okay, so I'm going to post this how you say la pauta, so you can have a look, and you can have a look at what you responded. um, I did receive like 5 tests like outside Canvas of people who had problems or who didn't have enough time. We're gonna try next time to keep that to a minimum. Ideally, I don't want to receive anything in my email because it's more transparent is if everything is on Canvas. So for next test, do allow some time to upload your responses, right? Um, so we can avoid that. Anyway, if there are no more questions, it's almost
Yo tengo una,
7. Yeah, tell me. Yes.
perdón.
Yeah.
El momento, la última pregunta, es igual a F por I.
Yeah. This is something that can be confusing. So let me take
Porque
a moment.
yo la había hecho como igual a cero. Entonces,
Well, it is the same. It is the same. It can be confusing, but look at the sum of torques has to be 0. It has to be. Otherwise, this thing would be moving, right? So so you could say, well, F1 times Y1 has to be equal to F2 times Y2. You could be tempted to do that, right? But then you're not taking into account this other force, which is the resultant force. And another way to look at this is that Y, let me rewrite this. Y, sorry, Y is F1 divided in F times Y1 plus F2 divided by F times Y2. So this is a weighted average of the two positions. Basically, you have one force acting here and another force acting here, and you know that there is one resultant force at some place, right? Uh, and that resultant force has to create the same torque uh, than these two competing forces. Have a look. It can be confusing. I find it a bit confusing. It's the same
No,
as saying yes.
no, claro, porque o sea, igualando cero no llegaba a nada.
Yeah, it's the same as saying, the sum. Oh, I'm sorry. The sum of forces has to be zero, but that doesn't mean that F1 is equal to F2, right? So what you're saying here is that is the sum of forces is F, right? And this is F1 minus F2. Because if this was zero, then these two should be equal, and they're clearly not equal. So the sum of forces is F, and the sum of momentum or torque is F total F times this arm, and this
Profe,
is F1. Yes,
que en la sumatoria, en la fuerza total, ¿no debería ser F2 menos F1?
it it just depends. It just depends on how you're defining your stuff, right? Uh,
Ah, claro, pero podía ser F2 menos F1 tomando los
yes,
ejes clásicos, porque al final para la derecha es positivo y para la izquierda es negativo.
yeah, yeah,
Ah, ya.
and then you could have said F1 is minus whatever acting on I. Yeah, that's great,
Ah, ya, perfecto.
of course. As long as if this is true, uh, then your reactions have to be plus something acting on Y too, right? I
Sí,
mean,
claro. También se puede comprobar que si soy consistente,
yeah,
la altura que tenía que calcular después me da positiva, no me da
yeah,
una altura negativa.
exactly. You have to be consistent. Here we are very very loose on the let's say on the Cartesian axis that we're working. I never said that this was X, right? So you could have put X wherever it was better for your. I only hinted that there was a symmetry plane because I think it makes things easier. But you could have put your X here. I mean, it doesn't really matter as long as you're consistent. So as long as you get the right magnitude at the right locations, then it's all right. I'm being asked. Yeah. I'm being asked if you just bear with me, and then we'll have a break. Okay. I think this is the last question. I'm being asked if I put in the test uh, that the application point it was H minus IG minus area IG. Is that right? Yeah, it's right. Because you're realizing that you're here. This is your reference level. But then this would be one, right? So this would be one. And then for two, you also had to use H big H. If you use H small, then you're gonna get a mess on your reference. Okay, but particular problems we can see them later on. But it's important that if you're comparing two distances, two values, they need to be in the same um, uh, reference, in the same system of reference, right? So you could have done it from the bottom up. I think it was easier, but you could also have done it from any point on the sky down. I mean, as long as it's consistent, you're gonna get to the same results. If you finally got to this h square minus h, I mean, yeah, cube, h square minus h square. If you got to this, then it's right. I don't really care how you got it. And here was something, right? Okay, hopefully that's clear. If not, give it a thought, and we can discuss it later. So let's take a 10 minutes break. I have 10:25 almost. So see you in 10 minutes, and then yeah, we can pick up our lessons for today. Okay. Okay. See you in a bit. Okay, let's return. Um, Before we continue with the class, uh, remember you have to turn in this assignment on Canvas and related to your writing skill on English. I said it on there, but if it's not clear, you have to write a very small argumentation of what you did or what you should have done, you think you should have done on the last homework. And it has to be on English. And somebody from the university is going to read this and say, okay, this student has an okay level of writing skill, or it's not satisfactory. And if it's not, going to be contacted and you're going to have to repeat this assignment. Uh, Again, it's not me who's going to grade this. You don't have to write a very long essay, just small argumentation of on why you did or why you should have done, and it has to be in for tomorrow. Okay, so don't let it pass. It is important for the course. Um, yeah. Any question about that? Is pretty clear or not clear at all? Okay, I'm gonna assume it's pretty clear. Some students already have turned in stuff, so uh, should be short to do. Okay, so don't let it slide. Try to do it as soon as possible. Okay, so we left last class we had. We started looking into differential analysis of flows, and you might remember what we got. We Differential analysis means writing the velocities and the pressures that represent the flow into differential form. You have the slides. I already put them online, but I'm not gonna go directly through them. I mean, you can read them on your own, but I'm gonna try to explain to you the key steps on the slides. Okay, so we left off from, we had a continuity equation, and we had momentum. This is why I don't like to talk about moment. I'd rather say torque, right? Momentum equations, and these were several on the three. Uh, so the continuity basically said for non compressive flow, you had the nabla of the velocity vector has to be zero, and this is just du dx times dv dy plus dw dz has to be zero. Um, as a question, since we're gonna get into many partial derivatives, are you familiar with this notation? If you put u sub x times v sub y times w sub z, do you recognize that this is a partial derivative? Have you seen this before? Yes, no? Yes. So I think this is shorter. So in the slides, in the book, you have the full derivative signs, but here on the whiteboard, I'm gonna try to use this if you don't mind, because I think it's just shorter. You use less ink, right? Okay, so this is continuity. A momentum equation in a very simplified form, you get the acceleration has to be equal to the general gravity field minus the pressure gradient divided by rho. And this was neglecting shear stresses. Okay, if you recall, shear stresses arise mostly due to viscosity. So if you say, okay, in a non-viscous fluid or flow, you get this type of equation. Of course, this is on x, y, and z, right? You can decompose them on these three components, and you get this equation. And remember, the acceleration has local acceleration, and then which is v sub t. This is the same as dv at 2 dt plus this is nabla. I might be wrong. I think it's nabla dot v, but it's basically, for x, for instance, you got, let me write this larger. You got u sub t times u sub x times v u sub y times w v u sub z. Okay, so this is the acceleration on x, on the x-axis, right? And you could do the same for all of them. Okay, and from these momentum equations, which are called Euler equations, which don't include viscosity, you could integrate the Euler equations into along one streamline, and then you get to the Bernoulli equation, right? I'm not going to write that down now, but that's more or less what we saw last time. So what we're going to do now is that we're going to add viscosities to it, and we're going to derive the full Navier-Stokes equations plus viscosity. Rather than viscosity, it's really shear stresses. Okay, so let's get to it. Let's imagine you have your classical Cartesian uh, uh, axis. We're going to call this x. For some reason, this is z and y upward, but it doesn't really matter. And then you have small volume of fluid right here. Okay. Previously, to obtain the Euler equations, we said, okay, let's consider only normal stresses on these infinitesimal fluid phases. Now we're going to consider all of the stresses. So in general, on a phase, you're going to have certain normal stress and two tangential stresses. Okay. And on this phase, I'm going to use another color. And in this phase, you're going to have this normal like this, and then you're going to have two tangentials. And we're going to call this is realize this has nothing to do with fluids. This is just normal stress analysis. The same yet that you can do in soil mechanics or in structural design. Basically, these are internal stresses. And we call them stresses because these are forces per unit area. And these are normally called sigma. And we're gonna call sigma ij. Okay. So sigma ij is a sigma that is acting on the y phase on the j direction. So for instance, this guy here should be sigma is acting on the phase normal to the z value, so this should be sigma z, and is acting on the x direction, should be sigma zx. Okay, this is just convention. Don't you're not supposed to memorize this, but the point is that on each phase you're gonna have one normal and two tangential stresses. Okay, and this is the way we can label them. Okay, now as always, we can assume, if this is a very small volume, we can assume that they vary linearly. The stresses vary linearly from one phase to another. So let's say, for the sake of the argument, here we have sigma xx, because it's the sigma acting on the x phase on the x direction, actually negative. What is going to be the value here? Well, it's going to be same that before, sigma xx plus the derivative of sigma xx with respect to x. Here I'm not going to use the x, it can be times this distance. We're going to call this, in the book you had a delta, but I'm going to use an actual delta, because this is clearer to me that this is a distance. Okay, so basically between one phase and the other, your variation is due to the unit size of the element and the derivative. I need to take a break of just 2 minutes, so please hang on. Okay, I'm back. Sorry about that, but it was the corner tube, and I'm alone at home, so I had to get the door. Okay, so what I was saying is that the stresses are gonna vary along this volume unit, basically on this amount. Okay, and so the net effect on the volume, if you take this uh, is the webcam working? Yes. So the net effect, if you subtract these two, you can see the net effect is only this one. Okay. So if you take only the normal, on this side it's going to be sigma x times delta. The sigma x at the x times delta x. All of this multiplied by the area of this phase, of these phases, which is delta
Profesor, una duda.
y, delta z. Yes,
Este cubito diferencial se está moviendo, ¿verdad?
that's a very good question. In this case, no, it's fixed. Now,
Ah, ya.
we could consider, it will depend. In this case, we're considering fixed, which is an Eulerian approach. So this is a fixed volume of the universe across which some fluid is passing. Okay. There are some other, when we did the streamline integration, we were actually following the flow, right? So in this case, it's fixed, but it's a good question.
Entonces es volumen estático, es agua estática nomás.
No, you do have velocities. You could have velocities. Actually, if you realize what we're doing here is that so far we're not getting into any fluid mechanics. This is just like a regular analysis. Okay, this is the same analysis that you would do in a piece of soil, for instance, which has no water moving. But at some point, we're going to use this, we're going to integrate, include these forces into our momentum equation. And this momentum equation represents the flow of motion, the motion of flows. So far, no motion is needed. But put a pin on that thought, because we're going to use it later on. Okay, so this is one force, and the other force, it will be just sigma xx time delta time, I'm sorry, this is delta y, delta z. and the other is just minus sigma xx times the same. I'm gonna use, I'm sorry for this, only delta volume. This is, let me just write it right. This is delta volume minus sigma delta volume. So you can see this is the force on one side and this is the force on other side. Now, this is not the only force acting on the x direction. You also have this guy and this guy and in the other sides, right? But from here it's clear that only the gradient will remain. So the net contribution to the forces acting on this small volume due to shear stresses are due to the gradients. Okay, so this is the key point. So if you sum all of the forces acting on x on the x direction, you're gonna get what I was showing before. You're gonna get well, sigma xx plus this gradient of sigma xx over x times delta x, all of these times delta y delta z minus sigma xx times delta y delta z, and you're also going to get okay, so this is sigma zx, and this one is sigma yx, and you're going to get similar values between this side and this side. You only have sigma yx plus the gradient of sigma yx over y in this case times delta x times delta y delta z minus similar stuff minus sigma yx delta y delta z, sorry, this was plus sigma zx times the gradient of sigma zx over z times delta c. Sorry, this is delta y, and this is delta x. This is delta x. This is delta x, delta y. Yeah. Minus sigma zx acting on delta x, delta z. Excellent. Okay, and here you cancel out everything, and basically what you get is that only the gradients are relevant. So you get the gradient of sigma xx on x times delta volume I'm going to use times the sigma of yx, sorry, yx over y times delta volume plus the gradient of sigma zx over z times delta volume. And from the same way you get to the other components in y and x. Of course, you can move the volume here, and what you get I don't know if to delete this, but well, basically what you get is that the sum of forces on x divided on the delta volume is nothing more than the gradient of sigma xx plus the gradient of sigma yx on y plus the gradient of sigma zx on z, and you get to the same ideas on y and z. Okay, which, yeah, I can just put here just to show you. Also, delta volume. In this case, it's going to be sigma acting on y on the x direction. which is the same. 2dx times sigma y on the y direction times sigma y z on the z direction, and so on. Okay. Now these are forces that we could include on our on our uh, uh, on our equation. Okay. You could realize here that this looks like a tensor. If you are, yeah, we have a nice question. They're being asked, isn't sigma xy isn't the same as tau? Yes, exactly. We'll get to that. But if you realize this is like a tensor, this is a matrix. I'm not gonna write uh, the third equation, but you get the hang, right? So this looks like a matrix in which you get d at the x, d at the x, right? D at the x. This is the y, the z. Here you have tensors, and yeah, the sigmas. They are just the shear stresses, not the normal ones. This is a normal one. This is a normal one, and the one I'm missing here is also a normal one. But the cross ones, they're exactly shear stresses. If you recall, from a fluid, let's say a fluid that is moving, we used to say, okay, there's a shear acting on that direction. So it's a normal shear. It's acting on that direction, normal to this surface, right? So all of the others are actually taus, okay? And what we could do in a matrix form, we could call the tau aj as a matrix of tau xx, tau yx, and tau zx. This is tau yy, and this is tau zz, and this is tau zy. And realize that this one here, tau xy, is symmetric to this one, and tau xz and tau xiz. This is symmetric to this one, and this one is symmetric to this one. Okay, so this is a matrix, and if we take the cross product of this matrix, we get exactly this one, this thing. So we can call all of this is just the sum of forces in a vertical in a vectorial form divided on the volume. Okay, and if that's so, we can just include this on our Euler equations. These are new forces that are acting due to the viscous effects. Okay, so let me just write this very succinctly. So you have that the acceleration is equal to the gravity field, the general gravity field. This guy is normally 0, 0 minus g, right? Minus 1 over rho of the gradient of pressure plus the gradient of the tau ij. So now we're adding the effect of the viscosity of this. This is called the viscosity tensor. And as somebody is pointing out, we know how these guys behave, right? Or we have an idea if the fluid is Newtonian, right? Okay, so these are the Navier-Stokes equations. Of course, you can decompose these guys into three main components. I'm sorry, this for this to be valid, the units have to be a row here. Okay, this row comes from this volume. Don't mind too much about that. Okay, so let me just write down one of these equations for x, just just to show you one thing. Okay, so for x, and taking the row down. So for x, we said before this would be u ut, the derivative of u with respect to time, times u ux times v uy times w uz plus g on x, which is normally 0, minus 1 over rho px, plus this new thing that we're adding now, which is going to be, yeah, here it doesn't work that nice. Tau xx, x, the derivative, plus tau yx, y, plus tau zx, z. And you have the same for y and for z. And that's it. These are the Navier-Stokes equations. These are used to represent viscous flows. Now, so we have the continuity equation and we have our extended momentum equation, which includes this this viscous term. Now, do you see a problem here? Let's say I tell you, okay, use these equations to compute something or to make a prediction of how a flow behaves. Well, the main problem here is that we have 4 equations because this is a vectorial form. So you have 3 equations here for x, y, and z. And you have the continuity equation. But you have too many unknowns. So you have the pressure, which is a scalar. You have u, v, and w, which are the 3 components of velocity. And then you have 9 components of tau. But really, well, since this is symmetric, you have 6 more components of tau plus 6 taus. So you have 10 variables and you only have 2 equations. I mean, 4 equations. So this is an over determined system. You can't really solve this. So you can't use it in anything useful. So in order to make sense of this, what we need to do, again, up until here, this is mostly let's say this is mostly dynamics. So the pressure, if there is pressure, you could take this out, and this is just internal, the internal distribution of the stresses. So in order for this to be fluid dynamics, is that we need to relate these shear stresses with the properties of the flow, which is the very same thing, the very fine thing that we did in the first one of the first lessons. Okay, let me try to make myself clearer. What we're gonna do is we're gonna say, okay, we know these are fluids, so we know these are flows. So what we're gonna do is that we're gonna relate the shear stress acting on y on the j direction with the properties of the fluid of the flow. So this is gonna be mu times the derivative of the velocity in I with respect to j plus the derivative of the velocity of j with respect to I. So basically, in the same direction, on the same plane, you're going to have 2 shear stresses due to the motion of the flow. of the fluid. And we're keep in mind that to do this, you need the fluid to be Newtonian. If it's not Newtonian, then you can't really relate your shear stresses with the gradients in velocity. Okay. And and if this is right, I mean, if this holds true, you end up with the following. You end up with the following. Again, I'm going to use only the x equation. So again, the acceleration is ut times ux times v uy times w uz. It has to be equal to g on x minus 1 over rho p sub x, or let me just dp at dx. And now we incorporate these guys. Mu over rho, because we divided everything by rho, times uxx. This is the second derivative with respect to x. Let me just, this is this thing. You can realize if you, I mean, you can do this math on your own. It's not really very important, but you can, if you insert this on the previous equations, you're gonna get to this equation. U with respect to y times the second derivative of u with respect to z. And these are the Navier-Stokes equations. Okay. So what steps did we use in order for this to use the continuity equations? We need this to be uncompressible fluid. In order to replace the shear stresses with the gradients in velocity, we need this to be Newtonian. Okay. And all of these forces are due to viscous stresses. These are viscous forces. So what we did before is that we say, okay, all of this we can say is just really pretty much zero. And then you get Euler. Euler are the equations when the viscosity is not very important. If viscosity is important because, for instance, mu is very high, let's say honey moving, or paint, or oil, stuff like that, then mu is pretty high. So these terms can be important. Or your gradients, this second order gradients are important. So these values can be large. Okay, so and these are Navier-Stokes equations. These are the equations that represent the full motion of complex fluids. For instance, Navier-Stokes equations are used to describe the shape and the motion of galaxies or any other fluid-like physics. I could and the cool thing is that you can fully represent your flow based only on the pressure distribution and the distribution of u, v, and w, or the three components of the velocity. Do realize that this equation holds true at every point where there is fluid at every time. So a solution for these equations are functions of the type of u, t, x, y, z, and the same for v, w, and p. So a solution is a field of u, v, w, and p, and it's a field on the full space, on the 3D space, and over time. So as you can imagine, these are complicated equations to solve. Actually, they don't have a numerical unique solution. You could become a millionaire if you come up with a solution for this. This is one of the, I think, 4 or 5 problems in mathematics that are still open. So an analytical solution of the Navier-Stokes equations is a current problem, is an open problem yet. So what we normally do, civil engineers and hydraulic engineers, is that we solve this numerically. And there's a whole field of that called computational fluid dynamics, which I will add that they also deal with turbulence. Turbulence. I understand that you have a turbulence course here at the university, but turbulence is it's a whole different animal. But more or less, you can you can assume that turbulence works like a kind of viscosity. So I'm gonna put this with very marked scarecrows. Uh, but don't mind about that. Later in the course, we're gonna do the distinction between turbulent flow, which for us turbulent flow is gonna be no viscosity, so only pressure gradients, and laminar flow, which is a flow where viscosity is so important that you have no turbulence. Um, in which case, this guy is going to be very important. Okay, so that's the derivation. I don't need you to memorize all the steps, but what you need to understand is that we are taking into account not only normal stresses, but shear stresses. And that those shear stresses, we're relating them to the properties of the flow because we know the flow is a fluid and we're assuming that it's a Newtonian one. If it wasn't the case, then we couldn't use the Navier-Stokes equations. Was that clear? Or are there any questions? Okay, so all clear. Excellent. What I want to do now is okay, this is all very nice, very theoretical, but how do we apply this thing? Okay, so I want to do an exercise. Okay, I'm going to take an exercise from the book, and I'm going to try to show you how we could use the Navier-Stokes equations. Okay, so for that, when should we have the next break?
Como en 10 minutos a las 18:24.
Okay, so let's have the break now. And in the meantime, I'm just going to write down the equations here in fully so you can have a look at them. And then, so let's return at 10 at I'm sorry, 18:24. Let's return in 10 minutes, and then we can work on this little exercise. It shouldn't take 20 minutes or so. Okay, so see you in 10 minutes. Okay, should be back. So hopefully everybody's back. Yeah, 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 no, I'm back. I'm okay. I took a 10-minute break. I don't know if you guys were. I was just writing this thing during the break, so I didn't expect anything following. Okay, so what I write down here, and I was doing this during the break, is because this is a long, really long equation, and it can be confusing, but it shouldn't. Okay, so this is the long version for each of the components. So this is x, this is y, this is z. But if you look at them, this is just the same as before. All of this before the equal sign, all of this is just the acceleration. So there's local acceleration and convective acceleration. This is due to actual change over time of the velocities, and this is due to change over space of velocities. And you can express this into vectorial form like so. So this is the local, and this is convective or advective accelerations. Okay, so this is accelerations. And at this side, we have the forces. These are the body forces due to the general gravity field. Normally, it would be only gravity, so only g going down. So this will be zero, this will be zero, and this will be minus g, right? But it could be. This is the general case, so it could be anything. These are also body forces, but due to pressure. So just like buoyancy, the gradient in pressure is what creates a force. So and a negative force. So it's a force in the opposite direction in which pressure is increasing. So if pressure increases downwards, then buoyancy goes up. If pressure increases to the side, then your flow is going to go to the left, right? So these terms, and up until here is Euler equations, right? These are Euler, which in vectorial form is up until here. Realize that all of these terms they're nothing more than acceleration, right? And now the new terms that we're adding is this viscosity terms. Viscosity. Sorry for the calligraphy; it's not the nicest. So and the viscosity terms, you can express them as I don't know the name of this operator, but the square nabla over the velocity. And here I'm just multiplying this with this Greek symbol nu. And nu is nothing more than mu divided by the density rho, which is here. So normally you can use just nu, just to avoid wasting ink. Okay, so these are the vectorial form of these equations, of the Navier-Stokes equations. Okay, is this clear for everyone? I know I already showed you this, but here I have the full equations. You can also read them on the slides, on Wikipedia, or on the fluid mechanics book. Okay, so I just took the time to write them down, and I think the vectorial form is pretty elegant. So it's a pretty short way to represent very complex phenomena. So I'm going to delete it though, because it's very elegant, but it's not very useful to what we want to do now. Okay, so there is I'm going to do a small exercise that you can find on the page 222 of the book. It's actually solved there. So I'm not doing anything pretty new here. But the idea is as follows. Let's say you have a certain tube, okay? And this thing has let me just, has a geometry of h and h from the center line. And we're putting x the x-axis on the center line. And again, for some reason, y is going upwards and z is going out. Maybe this should be, maybe z should be going up. I don't know. Doesn't matter. And we are being told, okay, we are being told that that this is a permanent flow. So permanent flow means no change over time. This is a viscous flow of Newtonian fluid, which is uncompressible. Okay, which, by it's no mistake, it's no coincidence. Those are all the assumptions we're using for developing these equations, except for the permanent one. But let's assume we have permanent flow. So the first question is, how do this? Yeah, permanent and steady flow is the same. Yeah, it's the same. Steady flow doesn't change. Permanent is. I might be wrong. Maybe permanent is the. I'm just in Spanish we say permanente. So maybe in English we don't say permanent. I might be wrong, but in English we do say steady flow. So that's for sure. So if we have steady flow here on this direction, on that direction, determine the simplified Navier-Stokes equations, and this should be the bed and uh, the bread and butter of this section of the course. Okay. So again, keep in mind that y is going up and z is coming out, which is weird, but I'm just stick with the notation of the book. So if this is steady flow, we can kill already everything that has a time derivative. So this should be zero, this should be zero, and this should be zero, right? Furthermore, we know that this is zero and this is zero because we're being told that gy is minus g. Okay, so y is going upwards, so this is minus g. Okay, we know that. And we also know that we have no flow on the z direction. So omega, w is zero, and therefore, and it's constantly zero. So all the w derivatives are zero. This is zero, 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 zero. And also all um, the elements that are multiplied by w are also zero. So this is zero and this is zero. Okay, so we already simplified this a lot. I'm sorry, this is it. So what you can see is that from the bottom equation on z up there, here we only have that dp at dz is zero. Dz. So here we have that p doesn't change on c, right? I mean on this direction normal to the whiteboard. So this equation is not really very useful. So we can just, throwing out of the window. But that's one of the equations. Okay, so we can't really neglect this, but we know this is zero because everything else is zero. Is that clear so far? I want it to be clear so I can delete this. Okay, I'm gonna assume it's clear. I can't undo on the billboard, so on the whiteboard. Okay, the rest of it. We know that we don't have vertical velocities. We're being told that all velocities is sideways. So we don't have vertical velocities. So this is also zero. This is also zero. And v is zero. This is zero. and all of this is 0 because we don't have vertical velocities. So the second equation, you end up with 0 is minus g minus 1 over rho dp of the y. Again, y is going up. So you might recognize this. This is just a hydrostatic equation, right? Is it clear for everyone? Basically, this is telling you that dp dp at dy is just minus gamma. Why pressure in the z-axis is 0, I'm being asked. Do realize that the pressure is not 0. The gradient, what is 0 is dp at this dz is 0. So yeah, because I already deleted, but all the acceleration was 0. And g, so a in z is 0. G in z is also 0 by definition. There is no acceleration laterally. And this whole bunch here, nu nabla square over z, this is also 0 because over w, because w is also 0. So the only term that you can't, you don't know a priori is the dp at dz, but it's the only one you got left. So it has to be 0. So that means that pressure doesn't change in this direction coming out of the whiteboard. Good question. Okay, and the second equation is just the hydrostatic one, right? So pressure increases over y proportional to gamma. Okay, which is what you expect. So no surprise there. I'm also going to kill this guy. Okay, so we're taking a lot of equations out. What else? Well, this also doesn't change because nothing changed in this direction. And realize that the velocity, if the geometry doesn't change in this direction, by continuity, yeah, all the gradients in x are also 0. All the gradients of the velocities. So this is 0, and this is 0, because the velocity profile is going to be the same along the tube, down the tube. What we can't know is how the pressure changes down the tube. So what we get is that the total acceleration is 0, which again is expected, because otherwise, if you had accelerating water, then it would be a time where water will collapse on itself or will separate itself. So you don't have acceleration on x because this geometry is uniform. To have acceleration, this should shrink. The area should be smaller. Then you would have an acceleration. Okay, so this is 0, and we have 1 over rho dp at dx plus mu over rho du at dy, right? We can just take out the rows just to make it clear. This is the equation that represents how the horizontal velocity changes over y. Okay, so these are simplified Navier-Stokes equations for this case. Okay, there might be another case, I don't know, painting flowing through a wall. I'm sorry, what? Why you can't kill the u at the y? Oh, well, because you don't know how u changes over y. You know that that u doesn't change on x because, like I said, the geometry is fixed. But and you know that u doesn't change on z because z is just the same. But you don't know how this changes, so you can't kill it. Maybe it's not that clear. Maybe I'm not being super clear. But think of it. Think of it like this. You know that you're gonna have some sort of profile. So u depends on y only, right? And this profile is going to be the same here and the same here. It has to be the same. If it changes, you're going to have acceleration, and you can't have that. So it doesn't depend on x, on z, or on time. Only depends on y. Therefore, you can't just neglect it. I'm sorry, this is minus. Okay, so this is the equation. And what are you can read it on the slide, but it says what are the boundary conditions? Well, boundary conditions are here at the at the boundaries. If you recall, what's u has to be here? U at y equals h 0, and u at y equals minus h has to be 0 too, right? We talk about this. This is a no slip condition. This is true. The no slip condition is true of all fluids. All fluids stick to the wall. So it's not true only for viscous fluids like this one, but every fluid. Even the water flowing on a river is stuck to the wall. The problem is that you have turbulence very near the wall, but that's another thing. But so the velocity here has to be 0. Okay, I'm being asked if this square root 2 is 0. Can I assume? I'm sorry. Let me just write this down. Otherwise, I can't really see it. If this is 0, you're saying, can I assume the y-dz is 0? Well, it's the other way around. We're saying this is 0, therefore it has to be 0 too. Okay, it's the other way. We know this, therefore this derivative has to be 0. If this is 0, of course this doesn't have to be 0. And actually, this is a concept that you don't know, and that depends on your boundary conditions. Okay. So, what do we do? What do we do now? We have the u at the y square has to be equal, to 1 over mu dp at dx, right? And we also know, because I deleted, but we also know that p is a function of y, right? So p is a function a certain p0. Well, if y is being measured like this, let me just write this down. So let me just give me a second so I can write this down more clearly. Okay, so I'm going to just delete this. Okay, so maybe that's clear, right? Okay, so we said the p at the y is just minus gamma. So pressure decreases upwards. This is right. And we have d square at the y is 1 over mu dp at dx, right? So yeah, we know the pressure from here. The pressure is going to be a function of y. So it's going to be a pressure at some point minus gamma y, right? This is just, integrating this over y. And if we integrate this, we get that the u at the y, sorry, okay, the u at the y has to be just this bunch, 1 over mu p at the x times y plus a certain constant. And if we integrate again, and we get that u as a function of y has to be this very same thing, y squared times c1 y times c2, right? And you could evaluate this in h and minus h equate to 0, and then you can solve this c1 and c2. I don't mind doing that right now, but yeah, you can do it. You can do it. That's not the core part. The core part is to realize that the full Navier-Stokes equations in a simplified scenario is yeah. You're right. Yeah. In a simplified scenario, there's going to be many terms that you're going to be able to neglect. Okay. And well, you can realize right away that if you don't neglect many, then these are really hard things to integrate. Okay. Okay, that's a very good question, and that's where I wanted to concentrate. I'm being asked, do we leave this thing just like that? Okay, what's dp at dx? dp at dx is the rate of change of pressure along x. X is this direction. So we're being told this is a tube that is horizontal. But in order for water to move, you need pressure here, let's say P2, you need this pressure to be larger than this one. Otherwise, water won't move, right? So dP at dx is actually what's driving the water, okay? And dP at dx, you could approximate this as delta P over a certain length. Let's say this is L. Okay, so it would be P2 minus P1 because P2 has to be larger divided by L. Okay. But that's a very good observation. I mean, there are going to be cases in which if you're not giving any more information, you don't really know what this is. Actually, in this case, we don't know. So we just say is the gradient of pressure, and we normally can call that, is a, if you recall the Bernoulli equation, this gives you an idea of the decrease in energy along this line. So energy here is smaller than here, and that's why water is actually flowing. Okay, so in this case we can leave it just like that. But yeah, it's a good observation. All right, and if you, I mean, you can look it in the book, and you can try doing this on your own. But you can solve these two constants based on these two boundary conditions. Of course, this is going to be symmetric. It's going to be something like that. Okay. And then what's interesting is that you can compute the full flow. We call flow, in Spanish is caudal. We normally use it with Q or small q, but Q is normally, well, by definition, it's just the integration of u, which depends only on y, over dy. Okay, and that this is going to give you an average velocity times an area. In this case, the area is just, if we do it per meter of width, it's just 2h. So you could compute the mean velocity. Okay, if you integrate this equation. This is just, a quadratic equation on y. So the average is going to be something like a factor of the maximum or something. I don't really recall, but the important thing is that you can get the flow integrating the velocity. And once you get the flow, if you divide it by the total area, you get the mean velocity. Okay, which is again a type of weighted average. So you have you have a lot of very small u's, and if you multiply each of them by their little areas and then divide for the full area, you get the average velocity, v. And if you multiply the average velocity times the area, you get the full flow. The flow is measured on cubic meters per second, for instance. So it's a volume. It's a volume over time. Has units of volume over time. Okay, this exercise is in the page 222. You can have a look at it. This is the core part. The rest is really just algebra. So I'm gonna leave that to you. And we are halfway through this this section of the course. Okay. So before I finish, let me ask: are there any question of the lesson today? What we did today? We talk about shear stresses. We added the effect of shear stresses over the equation of motions that we had already developed. And with that, we expanded the Euler equations, which are for inviscid flows, to the Navier-Stokes equations. We do include viscosity. Viscosity, real flows do have viscosity. So when viscosity is important, then we have to use the Navier-Stokes equations. And viscosity we included through these shear stresses, right? The exact math, I mean, you're not expected to develop this full everything step by step, but you need to understand the terms on the Navier-Stokes equations, and you need to be able to determine which terms can be neglected on a particular scenario. You're going to have one question of that on the test when the test comes, for sure. So I can tell you that. So any questions about today? Okay, no questions. So, antes de terminar, como les dije al principio, quiero dejar al final de las clases, o quizá al principio, no sé, quizás 5 minutos o lo que sea necesario, para preguntas que quieran hacer en castellano, si es que el inglés está complicando mucho, o aclaraciones que quieran hacer en castellano. Pueden ser de esta clase o de clases pasadas o de lo que vimos en la última clase. ¿No hay preguntas? Ok, entonces solo para cerrar, acuérdense mañana, tienen que enviar esta tarea de redacción en inglés. Es importante. Es requisito del curso, así que por favor, mándenla, creo que está hasta las 10. Si pueden hacerlo ahora, en verdad se demoran 10 minutos, por favor háganlo. Voy a subir la pauta de la prueba para que puedan revisar cuántos puntos tuvieron y el que quiera. Sí, me falta subir la clase pasada, la última clase, la tengo guardada, pero no he tenido mucho tiempo para ordenar eso, pero tengo que subir la clase pasada. Ya terminamos la unidad déjame ver, de kinematics. Y ahora estamos a la mitad de este análisis diferencial. Vamos a terminar el análisis diferencial la próxima semana. Y mi idea es que también hagamos un par de ejercicios en la clase. Y después de eso ya nos quedan solo 2 temas. Entonces, vamos en buen paso para la siguiente prueba, para quizá tener algo más de tiempo para hacer ejercicios en la clase. Así que yo administrativamente voy a tratar de ponerme al día mañana con las cosas que les debo. De todos modos, insístanme si es que no lo logro, pero debiera subir las pautas, debiera subir la clase, la última clase que tuvimos, y debiera subir esta clase. Eh,
Profe, suba también la pauta de la tarea 2, porfa.
sí, la voy a subir.
Como el output correcto, por así decirlo.
Sí, 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 les voy a subir todas las tareas, yo las genero con un notebook y después borro las partes. Así que les voy a subir el notebook que las generé. Eh, y un poco para darles más tranquilidad, para que no sea mucho esfuerzo y poco premio, vamos a tener solo una tarea más, ¿ya? Y voy a tratar que sea mucho más concisa, que lo que tengan que programar sea mucho más corto, cosa que no sientan que están dedicándole muchos días a algo que pesa muy poco, ¿ya? Eh, Eso. Así que, bueno, y de nuevo, cualquier comentario, sugerencia del curso, de las clases, yo no tengo ningún problema en la medida que sea razonable, yo me considero una persona razonable, así que si algo, como lo que hablamos ahora de las tareas, no tengo ningún problema. Eh, me preguntan qué pasa con la tarea de mañana si alguien no entregó la tarea 2. Esto creo que lo he dicho, pero por eso quiero tomarme el tiempo ahora. Si tú no entregaste la tarea 2, no hay problema. Igual vas a tener que leer de qué se trataba, qué era lo que había que hacer, y vas a tener que escribir en inglés qué es lo que hubieras hecho o cómo había que responderlo, ¿ya? Entonces, cuando preguntan, justifique su razonamiento, bueno, ahí tienes que decir en inglés, mira, acá lo que hay que hacer es esto, esto, esto. Da lo mismo si no lo hiciste, da lo mismo si no entregaste la tarea, ¿ya? Eh, yo quería en esta tarea evaluar las dos cosas, pero efectivamente, como me hicieron ver, la tarea salió más larga quizás de lo que todos queríamos y mucha gente simplemente no la entregó. Entonces eso significa que se quedó sin evaluar esta parte en inglés, ¿ya? Entonces ahí quizás fui poco estratégico o pensé que se iba a demorar menos, no sé, salió más largo de lo que yo esperaba.
¿Opinión? En la explicación como del razonamiento, yo puse igual algunas como cosas como matemáticas, como no sé, esto es gamma por A por H, por ejemplo. Eso lo dejo así, no es necesario que ponga área por altura, por... Puedo dejar fórmula en el razonamiento, ¿no?
Sí, sí, sí. Por
Ah,
eso
ya.
digo, el razonamiento lo va a revisar, no tengo idea, el profesor de inglés de la universidad, tengo el nombre ahí, pero en el fondo da lo mismo de lo que estés hablando. Lo importante es que la redacción esté correcta, ¿ya? Así que no hay problema en que dejen la fórmula, no hay problema en que hablen. Así que eso no es lo relevante. Lo relevante es que hablen, algunos de ustedes también, por ejemplo, me dieron el razonamiento en castellano. Entonces, a lo mejor yo no me expresé lo suficientemente bien, pero eso, si es que eso no lo puedo evaluar en el fondo, en el nivel de inglés. Así que por eso decidí, ok, separemos esta cuestión, si alguien no entregó la tarea está bien, entiendo que es mucho castigo, o sea, mucho esfuerzo para poco premio, no hay problema, pero sí tienen que entregar esta cuestión porque eso no lo evalúo yo. Me dicen para la próxima homework hacer un PDF como este que debemos entregar hasta mañana. La próxima tarea igual va a ser un notebook. Eh, lo que decía al principio de la clase es que quizá no se la voy a mandar el fin de semana para que no pierdan ese fin de semana. Eh, Me comprometo a hacer solo una más, así que con eso ya no tienen esa incertidumbre cuántas más podían ser. Y me comprometo a que sea algo mucho más concreto, o sea, rellenar solo un par de cosas más claras. Pero sí es importante que hagan el cálculo y que su notebook yo lo pueda correr, porque con eso puedo ver que el cálculo está hecho. Y para esa tarea no va a importar mucho la explicación, ¿ya? Así que
Los
no va a
notebooks se
ser
pueden,
necesario. ¿Cómo?
las tareas se pueden recorregir.
Todo se puede recorregir, yo entiendo,
Ah,
así que
ya.
no hay problema. Si alguien sí, preguntan si es que pueden haber más tareas con puntos extra. También lo he pensado un poco, veamos cómo van las notas. Hasta ahora, como te digo, la nota de la primera prueba está más o menos mala, creo yo. No sé cuál es el estándar de qué porcentaje de los cursos termina bajo 4. No tengo ese número, no tengo idea. Pero yo espero que las siguientes pruebas haya un repunte. Y ahí podemos ofrecer a lo mejor alguna tarea adicional para sumar puntos, por ejemplo. O que el homework sea mucho más concreto, cosa que tengan tiempo y ganas de hacer algo más para sumar puntos adicionales. Pregunta Daniel si está la pauta. No está la pauta, la voy a subir. Las correcciones fue bien aleatorio. A algunos se les comentó, a otros no tanto. No fue algo muy consistente. Salvo, no sé, cosas muy puntuales. Así que voy a subir la pauta, como les digo, mañana, yo creo, para que ustedes todas la puedan ver y todos puedan mandar a recorregir si es que consideran necesario. Eh, Eso, así que ese es un poco el panorama, ¿ya? Así que todas las clases les voy a partir con 10 minutos para que hagan más preguntas en castellano. Yo a veces me siento hablando solo, yo me imagino que están ahí escuchando, pero claro, si a lo mejor a uno le cuesta un poco el inglés, eh, puede ser complicado. Entonces, quiero dejar estos 10 minutos al principio y al final, para que si tienen dudas, las hagamos en castellano, no hay problema, para que no sea intimidante solo la barrera del inglés. Lo de las recorrecciones, voy a publicarlo también. Me comentaban ahora en clase que no hay una forma correcta. Entonces lo que vamos a hacer es que las recorrecciones las voy a ver yo. Así que las recorrecciones me mandan un correo a mí, el que quiera recorregir. Lo voy a comentar de nuevo, aunque lo dije al principio de la clase. Cualquier cosa que yo recorrija, no me voy a basar en la pauta anterior, ¿ya? Sino que voy a agarrar lo que me están mandando y lo voy a corregir como si lo corregía por primera vez, ¿ya? Eh, Algunas
¿Puedes
preguntas dicen,
en el chat? ¿Subir en el chat?
sí, igual, mira, lo voy a escribir, pero mi correo tiene que estar en la sección de contacto o en la página de inicio. Voy a hacer, ¿eh? De hecho, tengo un correo acá. Ya. Alguien dice, ¿cómo puedo saber si me revisaron la pregunta? Algunas personas me preguntaron que verificara si es que estaba subido. En general, si a alguien no le quedó subido, yo lo contacté, le dije, oye, ¿qué pasó? ¿No lo subiste? Así que es, a todo el mundo se le debería haber corregido. Creo que muy pocas personas, puede ser una, no respondió nada, ¿ya? Así que, y mucha gente al final de la prueba también me pidió que verificara si es que estaban subidas las cosas, ¿ya? Así que si tienen dudas, ahí tendría que mirar en Canvas. Quizás ustedes van a poder ver también los archivos que subieron. Déjenme revisar la prueba porque, como lo he dicho un par de veces, yo no estoy tan familiarizado con Canvas. Entonces, tengo que hacerles disponibles las respuestas alternativas para que ustedes las puedan ver. Y quizá la de desarrollo también van a poder ver el archivo que subieron. Y ahí van a tener claro si es que se les corrigió o no. Eh, Eso, pues, solo comentarles de nuevo, a mí me interesa que aprendan, me interesa que pasen, todos, ojalá, pero todos vamos a tener que poner esfuerzo. Yo, para ser súper honesto, no vamos a regalar las notas ni subir las escalas solo por subirlas. Así que yo quiero poner toda mi parte para que ustedes aprendan lo más posible. Y ustedes, por su parte, también, si el curso es más difícil, quizás van a tener que ponerle más. Si les cuesta mucho el inglés, quizás van a tener que leer 2 o 3 veces la misma materia. Es lo que nos toca un poco a todos. Entonces yo estoy dispuesto a ayudarlos en lo que pueda y un poco lo que estoy diciendo ahora es, van a haber menos, solo una tarea, va a ser programación mucho más acotado y vamos a tener este espacio para que hablemos en castellano solo para aclarar dudas. En el fondo, todo el curso sigue siendo en inglés, pero vamos a dejar este espacio para que vayamos aclarando dudas en castellano. Más, no sé, pues, algunas cosas que puedan proponer o que se nos vaya ocurriendo en el camino. Eh, Eso. Nos vemos el otro lunes, si es que no hay más preguntas. Y ustedes tienen ayudantía este jueves, ¿ya? Así que ahí también pueden comentarle al ayudante, no sé, qué tipo de preguntas les gustaría. Los invito también a que propongan, oye, este tipo de cosas me gustaría ver, o traté de hacer este ejercicio del libro y no me salió. Ese tipo de cosas nosotros las vamos a recibir con muy buen agrado. Así que también los motivo a que por su lado también nos pongan presión en el fondo. Así que eso, muchachos y muchachas, estamos por hoy día, creo, ¿no?
Profe, acuérdese también de liberar las respuestas del examen de la prueba,
Sí, sí.
que todavía están escondidas.
Mañana me voy a poner al día con todo lo administrativo, espero. Y si no lo hago, eh, mándenme correos, moléstenme, no hay problema. Hoy día no puedo, mañana voy a tratar.
Ya, muchas gracias, profe, chao.
Perfecto, chao, chao.